second lecture on Hermite differential equation, we discussed about the Rodriguez formula. Rodriguez formula is that Hn of x is equal to e to the power plus x square dn dx e to the power minus x square. This is the Rodriguez formula, and we then discussed generating function. These two things we discussed in the last class. Now we need to find out the recurrence relation, that is the relation between the Hermite polynomial of different orders from this equation. We differentiate this partially with respect to t. So del g del t is equal to 2x minus t g of xt, and when we differentiate this with respect to t, we get t to the power n minus 1 factorial hn of x, and for this we again use such an expansion, twice x minus t summation over m This is an identity in T. So if we collect the coefficient of T on the left and right of a particular power of T on the left hand side, and that should be equal to the coefficient of T to the power, that power on the right hand side. We equate the coefficient of T to the power k on both the sides. So this term will when this is multiplied by x, and the term will contribute to t to the power k when n is equal to k. So this is hk of x by k factorial, and obviously there is 2. And the second term, when t is multiplied, so the power is t to the power m plus 1. So in that case, m plus 1 should be equal to k, that is n is equal to k minus 1. So this is minus 2 h of k minus 1 of x, k minus 1 factorial. And this term will contribute to t to the power k when n minus 1 is equal to k, that is to say n is equal to k plus 1. So this is h of k plus 1 of x, h of k plus 1 of x by k factorial. Now if we adjust the denominator, then we find that 2hk of x minus 2k h of k minus 1 of x is equal to hk plus 1 of x. This is one recurrence relation which relates Hermite polynomial of different orders, and we can use these to find out Hermite polynomial of higher order. Let us start with the fact that h0 is equal to 1 and h1 is equal to 2x. If we put this k is equal to 1, then we get h2 with k is equal to 1, h2. So this is 2 into h1. Sorry, one x is missing. So there is an x factor. So this is 2x h1, 2x h1, and then k is equal to 1 minus 2 h0. So this is 4x squared minus 2. We can use a k is equal to 2 in this equation. So this is k h3. h3 is equal to twice x h2 minus 2 into 2 h1. So this is 2x into h2 is 4x square minus 2, and this is minus 4 into 2x. So this is 8x cubed minus 4 and minus 8, 12x. In such a way we can generate Hermite polynomial of still higher orders using this recurrence relation. So this is one important recurrence relation of Hermite polynomial. This is hk plus 1 of x is equal to twice x, hk of x minus twice k, h of k minus 1 of x. Now, if we differentiate this generating function with respect to x, then we will get an expression on the left, and on the right hand side we will get the derivative of the Hermite polynomial. So that will give you the, the derivative of the Hermite polynomial in terms of the Hermite polynomials. So let me first differentiate this with respect to x. So this is del g del x is equal to twice t times g, and on the right hand side we will have n is equal to 0 to infinity t to the power n factorial h n prime of x, where h n prime means the derivative of Hermite polynomial with respect to its argument. We replace this g by another such expression, so we get twice t summation over n is equal to 0 to infinity t to the power m factorial h m of x is equal to summation over n is equal to 0 to infinity t to the power n factorial h n prime of x. So again, this is an identity in T. So the coefficient of a particular power of T will be same on the left as well as on the right hand side. So coefficient of T to the power k. This term will contribute to T to the power k when n plus 1 is equal to k. So when n plus 1 is equal to k, so n is equal to k minus 1. So h of k minus 1 of x and in the denominator we have k minus 1 factorial, because n, and this term, this contributes when n is equal to k. Factor is missing. another relation involving the derivative of the harmonic polynomial. So if we want to find out h prime of 1 from this relation k is equal to 1, so it is 2 times h0, 2 times h0, that is 2. Note that h1 is 4x, h1 is 2x. So when we differentiate it with respect to x, it is simply 2. We use this for the calculation of h2 prime. h2 prime as per this relation is 4 h1. So h1 is 2x. So this is h1 is 2x. So this is 8x. Remember that h2 is equal to 4x square minus 2. So when we differentiate it, it is 4x. So this formula gives you the derivatives of Hermite polynomial, and we write h prime of k of x is equal to 2k. You see that there is the same factor. So if we use this relation in the first, we get hk plus 1 of x is equal to 2x, h of k of x, and for this we write h prime k of x. So this is 2x minus gdx operating on hk of x. We know that h0 is 1, so we can write it as this is another Rodriguez type formula for Hermite differential equation, and it is very useful in calculating Hermite polynomial. As for example, h0 of x is, this part is to the raised to the power 0, so this is 1. h1 of x is equal to 2x minus gdx operating on 1, so this is simply 2x. h2 of x is equal to 2x minus gdx operating twice on 1, so this is equal to 2x minus gdx operating on 2x, so this is 4x squared minus 2. So this is another Rodriguez type formula for Hermite polynomial. Now, with this, these are few calculations and derivations of Hermite or recurrence relation of Hermite polynomial. Now, in the earlier class, we have derived Rodriguez formula by successive differentiation. We can also derive Rodriguez formula starting from the generating function itself. The generating function of Rodriguez Hermite polynomial can be written as summation over k is equal to 0 to infinity t to the power k a factorial hk of x, and on the right hand side this is g of xt, which is equal to e to the power is equal to t minus x. This is simple manipulation. We differentiate this relation in time successively with respect to t. Now so del del t is equivalent to del u. With respect to t. So this is t to the power k factorial, and when we differentiate it n times, so this will be k into k minus 1 right up to k minus n plus 1 e to the power k minus n hk of x, and the differentiation gives you x square del n del un to the power minus u square. Now consider the left hand side. The k ranges from 0 to infinity. So basically the term involves t to the power 0, then t to the power 1, t to the power 2, etc. If we consider n to be 2, then all these terms will go to 0 as they are being differentiated more than this is when this is differentiated twice, it is 0, it is 0. So all the term with k less than n will go to 0 when it is differentiated. So we can write it, actually this sum is up from k is equal to n to infinity. Now we set t is equal to 0. We set t is equal to 0, in which case u becomes minus x, because u is equal to t minus x, and t is equal to 0, u is minus x. Then in this series, all the powers of t with k greater than n will be 0. Only the term with t is equal to n will have t to the power 0, which is independent of t, and it will survive even for t is equal to 0. And in which case this is also k factorial, this is also, that is the numerator and denominator both are equal to n factorials. Now let me explain the simplification once more. When we differentiate this successively n times, the result is this one. Now all the terms with k less than n will go to 0 when it is differentiated n times, and as we set t is equal to 0, all the terms having power of with k greater than n will be 0 due to this fact, and only the single term with k is equal to n will survive, and in which case this part is 1, because both numerator and denominator are equal to factorial n, and in which case we get left hand side hn of x, and on the right hand side we have x square, then del n, this del of minus x to the power n, and u is minus x square. Since there is no other derivative variable other than x with this restriction, we may replace the partial derivatives by the total derivative, and this becomes minus 1 to the power n dn dxn e to the power minus x square. So this is an alternative derivation of Rodrich's formula using the generating function. Now with this we go to the orthogonality property of Hermite differential equation. In the case of Legendre polynomial, we have seen that the Legendre polynomial form a orthonormal basis in the range g minus 1 to plus 1. In the case of Hermite polynomial, the situation is something different. Here the region of interest extends from minus infinity to plus infinity. And there is another difference is that there will be a weight factor appearing in this case. So first let me just justify the appearance of weight factor. So we are studying our discussion on the orthogonality property of Hermite different polynomial. Orthogonality of Hn of x. Let us consider Hermite polynomial of order m, which satisfies the differential equation. I am omitting the argument. And another Hermite polynomial of order n. We multiply the first one by hn and second one by hm and subtract second one from the first. So we get hm double prime hm minus hn double prime. This is from the first term. Minus twice x hm prime hm minus in the case of Legendre polynomial, there was a factor 1 minus x square and there was a factor 2x. If we differentiate this part with this, and if we define a function capital Y is this, then the derivative of capital Y is nothing but this. So we can write it as dy dx minus twice x y is equal to 2n minus hm. Now note that this is not integrable. The left hand side is not an exact differential. Was an exact differential for Legendre polynomial. I want to make the point clear once more. In that case, this was del y del x minus twice x y. So which could be written as ddx of 1 minus x square y for Legendre. For Pn, but it is not possible. We could say that the Legendre this corresponding expression for the Legendre differential equation, the left hand side were an exact differential, but it is not an exact differential. But we could make it by introducing the integrating factor. because this differential equation is of the form dy dx plus p of x y is equal to some q of x. So that if we know that the integrating factor is e to the power lambda, and lambda is equal to p dx. Here p is equal to minus 2x, so lambda is equal to minus 2x dx is equal to minus x square. So the integrating factor is equal to e to the power minus x square. So this is the first step. So this part, this equation is not an exact differential, the left hand side. But if we multiply it by this factor, it becomes an exact differential. So towards this, we multiply both the sides by e to the power minus x square. So we multiply it. In or this part is written as when we differentiate y, this is, and when we differentiate this one, it is minus 2x. So we now integrate this expression between limits plus minus infinity. So we integrating, we get capital Y dx from limit minus infinity to plus infinity. On the right hand side we have 2 n minus m and then this part hm of x, hn of x e to the power minus x square dx integrated from minus infinity to plus infinity. Now, so this d of this thing. Now this part is 0 because y is a finite quantity and this part goes to 0 at plus minus infinity. So the left hand side is 0 and the right hand side is this one. So we conclude that for m not equal to n, we have integration from minus infinity to plus infinity hmx hnx e to the power minus x square dx is equal to 0. So we say that the Hermite polynomial of two different order, since m not equal to n, so Hermite polynomial of different order are orthogonal with respect to weight factor e to the power minus x square. But what happens to the case when m is equal to n? The situation m is equal to, for m is equal to n, this factor itself is 0, so this part may be 0 or may not be 0. So the normality condition, that is when m is equal to n, the normality condition cannot be obtained from this expression. So we will use the generating function for the evaluation of a normality condition. Once again, note the appearance of integrating factor in the curves of Hermite polynomial. These were not there in the case of Legendre. In, in the discussion with Logar and Bessel function, we will also find that there will be an integrating factor. So the conclusion is this that the Hermite polynomial of two different orders are orthogonal in the limit plus minus infinity, subject to a subjected to a weight factor e to the power minus x squared. We use Hermite this we use g of xs and g of xt. So we use two generating function with parameter, one with parameter s, another one with parameter t. So this is twice sx minus x square. This is twice tx minus t square. And on the right hand side we have summation over m is equal to 0 to infinity. For this one it is s to the power m factorial hm of x, and for second one we write m is equal to 0 to infinity t to the power n factorial hn of x. We multiply both the sides by e to the power minus x square and rearrange the term. So on this is summation over mn s to the power m t to the power m factorial n factorial, then e to the hm of x hn of x e to the power minus x square. And on the right hand side we have e to the power twice sx plus twice tx minus s square minus t square minus x square. We rearrange this as whole square, so the term is minus, and so x minus s minus t whole square is equal to x square plus s square plus t square minus 2sx minus 2tx plus twice st. So this term is an additional term. So this term has to be adjusted. So this is twice st. This term has been adjusted. Now we integrate both the sides. So we rewrite it to be to the power twice st e to the power minus u square, where u is equal to x minus s minus t. Then we integrate this result from minus infinity to plus infinity. So we have hn e to the power minus x square dx from minus infinity to plus infinity. This part is delta mn as we have already seen, and this is e to the power 2st is out of integration, and we will have e to the power minus u square du from minus infinity to plus infinity. This integration, if we introduce z is equal to u square, then this is minus z, and u is equal to z to the power half, so then du is equal to half z to the power minus half dz. So this side can be written as e to the power 2st. We write it e to the power minus z, and for du we write half z to the power minus half dz, and the integration was from minus infinity to plus infinity. Since it is an integrandism, we write it from 0 to infinity with a factor 2, and so this half cancels with this, and this is gamma of half, this is root 2, and root pi, so this is pi times e to the power twice st on the left hand side, and right hand side, and on the left hand side we will have single sum. N is equal to 0 to infinity st to the power n factorial n square in the hn square of x e to the power x square dx is equal to root pi e to the power twice st. We expand it in Taylor series. K factorial. So if we equate the coefficient of st to the power some particular order, say L, so we get on the left hand side 1 upon L factorial square from minus infinity to plus infinity HL square of x e to the power minus x square dx is equal to root pi 2 to the power L factorial. So, HL square of x e to the power minus x square dx from minus infinity to plus infinity. This is pi 2 to the power L factorial. This is the normality condition. So the orthogonality condition and normality condition are clubbed together to get the orthonormality condition of Hermite polynomial is like that. Integrated from minus infinity to plus infinity, hn of x e to the power minus x square dx is equal to this is the orthonormality condition. It is one can verify the relation for few low order Hermite polynomial. Let us verify the orthogonality condition for few Hermite polynomials of low order. So we shall use the relation involving 1 and 2. We define the integrand mn is equal to from minus infinity to plus infinity hnx e to the power minus x square dx, and we use h0 is too trivial, so this is 2x and h2 is equal to 4x square minus 2. So we first I11. So limit is from plus infinity to minus infinity, h1 square of x e to the power minus x square dx. So this is 4x square we can write it as 8 dx. We use the substitution that x square is equal to z, so that dx is half z to the power minus half dz. So this becomes 4 z to the power half e to the power minus z dz 0 to infinity. This is gamma of 3 by 2. Gamma of 3 by 2. 4 times gamma of 3 by 2. So we know that gamma of n plus 1 is equal to n times gamma n. Here we write gamma of 3 by 2 is equal to gamma of 1 plus half. So this is half times gamma of half. So this is root pi by 2, as gamma of half is root pi. So this is 2 root pi. We put n is equal to 1 in this expression. This is n 1 factorial 1, 2 to the power 2. Sorry, this should be pi. And we see that the result matches with this expression. Now we consider h12. I12. This is equal to dx. As the integrand is odd, the result is 0. Finally, the result is from minus infinity to plus infinity, 4x square minus 2 square into the power x square dx. First thing, we write it as 2 and then put the limit from 0 to infinity as the integrand is open, until we have 16 x to the power 4 minus 16x square plus 4 to the power minus x square dx. So this is 2. This is 16g z square minus 16z plus 4 to the power z minus z, and dx, for dx we write half z to the power minus of dz. This half cancels with this 2 and the result is 16 z to the power 3 by 2 minus 16 z to the power half plus 4 z to the power minus of to the power minus z dz. This is 16 times gamma 5 by 2 minus 16 times gamma 3 by 2 and then 4 gamma half. Now we have earlier obtained that gamma 3 by 2 is equal to half times root pi, and gamma 5 by 2 is written as gamma 1 plus 3 by 2. So this is 3 by 2, gamma of 3 by 2. So this is 3 by 4. So this is 16, 3 by 4 minus 16 times half plus 4 times root pi. This is equal to 8 root pi. Compare the factor that it was root pi 2 to the power n factorial. So this is 2 to the power 2, this is 4, and 2 factorial is 2, 8. So we get the correct result for h is equal to h1 and h2. Another interesting fact of the appearance of this part is that if we try to integrate only the Hermite polynomial without this weight factor, we find that the integrand diverges. So the Hermite polynomial, integration of Hermite polynomial or multiplication of Hermite polynomial of two orders do not converge. So the result is a finite one only when one introduces the weight factor.